Howdy. This video is on the temperature dependence of equilibrium constants. Most reactions are temperature dependent. To be able to optimize conditions for a reaction, it is important to understand the reaction's temperature dependence. An equilibrium constant, remember, is a specific constant for a specific reaction. If you change the temperature, typically you change the equilibrium constant. After watching this video, you should be able to relate the temperature dependence of an equilibrium constant to Le Chatelier's principle. You should be able to predict whether the equilibrium constant will increase or decrease with increase in temperature for a reaction. Given the equilibrium constant at one temperature, you should be able to calculate the equilibrium constant at another temperature. And so previously we talked about Le Chatelier's principle. Le Chatelier's principle says that if a system is at equilibrium and is disturbed such that Q no longer equals K, then the system will counter the disturbance to get back to equilibrium. And so we saw that adding a reactant to a product or removing a reactant product might change Q. Changing the volume of the reaction chamber might change Q. Changing the temperature will probably change K. So what will happen if the following system's at equilibrium and then the CO2 pressure is raised? Well, according to Le Chatelier's principle, if we're at equilibrium and then we increase the CO2 pressure, that should produce more CO2 aqueous. And so if we look at it, that's exactly what happens. Gases are soluble in liquids. They follow Henry's law. So the solubility of the gas in liquid is equal to a constant times the partial pressure of the gas. And so here we have solubility on the y-axis, pressure on the x-axis. As you increase the partial pressure of the gas, you increase the solubility. What happens if the following system is at equilibrium and then xenon gas is added to increase the total pressure? Well, xenon gas is not in the equilibrium expression. It's not in the expression for the reaction quotient, and so we would expect nothing. Xenon gas is inert. It's a noble gas. What will happen if the following system is at equilibrium and then the temperature is raised? And so this reaction is exothermic. Heat is a product, and so if you raise the temperature, it's like adding heat, and so we should expect that the equilibrium will shift towards the left, and so more reactants will form. And that's exactly what we see. If you get soda pop warm, it actually loses some of its fizz because some of the CO2 goes from solution into the atmosphere. For this reaction, does the equilibrium constant increase or decrease with increase in temperature? So higher temperature, we're producing more reactants. Equilibrium constant's products over reactants. And so if we produce more reactants, we'd expect the equilibrium constant to decrease with increasing temperature. And so for exothermic reactions, higher temperature always corresponds to smaller equilibrium constant. For endothermic reactions, higher temperature always corresponds to increasing equilibrium constant. Will the following equilibrium shift towards products or reactants with an increase in temperature? And so it gives us a delta H. Remember, delta H is equal to Q, a heat transfer to the system under constant pressure and expansion work. And so delta H is positive, and so that means heat's being transferred to the system. So this is an endothermic process. So heat would be a reactant. And so we should expect that higher temperature would cause more products to be formed. So again, for endothermic reactions, heat's a reactant. Higher temperature always corresponds to an increase in the equilibrium constant. Will the following equilibrium shift towards products or reactants with an increase in temperature? Here we have delta H negative. And so again, delta H is equal to Q, heat transfer to the system under constant pressure and assuming no expansion work. And so Q is negative, so that means heat is going from the system to the surroundings. And so this is an exothermic process. So for exothermic processes, adding higher temperatures like adding heat, and so you'll produce more reactants. For exothermic processes, higher temperature always corresponds to a smaller equilibrium constant. Will the following equilibrium shift towards products or reactants with an increase in temperature? And so notice that we're going from a gas to a liquid. You should remember that the enthalpy of a gas is always higher than the enthalpy of the liquid. If you want to go from liquid to gas, you have to add heat. And so heat will be a product. And so that is an exothermic process. And so higher temperatures like adding heat and will form more reactants. So ECM systems are dynamic at the atomic level. Always reactions are occurring. Even at equilibrium, you have the concentrations seem to be constant, but you still have the forward and reverse reactions. It's just that the rate of the forward reaction equals the rate of the reverse reaction.
At room temperature, a solution of cobalt chloride is pink in color. When we heat it, it gradually turns blue. If we then cool the solution in an ice bath, it turns pink again. The reaction reverses.
And so the pink compound is more stable at low temperature, and the blue compound is more stable at higher temperature. And so by changing temperature, we can actually go back and forth on this reaction. And so at high temperatures, the products are more stable. They have a lower free energy than the reactants. At low temperatures, the reactants are more stable. They have a lower free energy than the products. So at high temperatures for the reaction below, delta G naught would be less than 0. So at high temperatures, this is a spontaneous reaction. K would be greater than 1 because we'd have mostly products. At low temperatures, the reactants are more dominant. And so delta G naught would be greater than 0, and K would be less than 1. And so is the reaction exothermic or endothermic? And so the products are more stable at high temperature, and so that means heat must be a reactant. And so that would correspond to an endothermic reaction. And so it's kind of interesting. We can think about it as at low temperature, our plot looks like this. Reactants are more stable. And then as you increase the temperature, what's happening is the reactants free energy is going up, the products free energy is going down. The minimum is going to higher Q. So does that ECM constant increase or decrease with increase in temperature? And so we saw that this is an endothermic process. Heat is a reactant. Higher temperatures like adding heat, we're pushing it towards the right. We're getting more products. ECM constant's products over reactants, and so the ECM constant should increase with increasing temperature. So endothermic reactions, K increases with increasing temperature. Exothermic reactions, K decreases with increasing temperature. So here we have another reaction. We have O2 going to N2O4.
Nitrogen dioxide, a reddish-brown gas, is formed when nitric acid reacts with copper. The gas is poisonous and must be handled carefully. Even small quantities can cause irreversible lung damage. In a closed system, nitrogen dioxide exists in equilibrium with dinitrogen tetroxide, which is a colorless gas. At a given temperature, specific concentrations of each gas will be present in the system. When the tube is chilled, the concentration of dinitrogen tetroxide increases, and the concentration of nitrogen dioxide decreases. When the tube is heated, the concentration of reddish-brown nitrogen dioxide increases, while the concentration of dinitrogen tetroxide decreases.
So it's kind of a cool reaction. And so what we see is that the brown one here is our reactant. And so that's more stable at high temperature. The colorless one is our product. It's more stable at low temperature. So high temperature favors the reactant. Does that mean it's an exothermic or endothermic reaction? Well, that means that heat must be a product. Higher temperatures, like adding heat, pushes it towards the left. And so that would be an exothermic process. Now we can actually look at our delta H's and delta S and delta G. And so delta H is minus 57, consistent with it being exothermic. Delta S is minus 176 joules per Kelvin. And remember, delta G equals delta H minus T delta S. And so we can actually find the temperature at which it goes from being spontaneous to being non-spontaneous by setting delta G equal to 0. And so at the transition temperature, delta G is 0. We can solve for T. And that would give us T is equal to delta H over delta S. Now remember, the energy units have to cancel, and so I converted entropy into kilojoules from joules. So I just moved the decimal point over 3. And remember that reactions are only temperature dependent in terms of spontaneous or non-spontaneous if they have the same sign, because temperature has to be positive. So the negative signs cancel. And we get 324 Kelvin for the transition temperature. So at 324 Kelvin, delta G naught equals to 0. We call that a reversible process. K is equal to 1. Higher temperature, again, remember that favors our reactant. And so delta G would be positive. That would be a non-spontaneous process. K would be less than 1, and we'd say the reaction was reactant favored because they have mostly reactants at equilibrium. And then if we look at low temperature, it favors our product. And so that means delta G naught is less than 0. Remember, the lower the free energy, the more stable. Then the reaction would be spontaneous. K would be greater than 1, and that would be product favored. And so you can think about it at temperature greater than 324, you're mostly looking at the reactants. It's reactant favored. And then as you raise the temperature, the minimum actually goes towards the right. We can look at the Ekman constant as a function of temperature. And so as you increase the temperature, Ekman constant goes down dramatically. And it makes sense because our delta G is actually, e to the minus delta G, and so it goes exponentially down. And so again, here we have our K. If we take, K equals e to the minus delta G over our T, remember delta G equals delta H minus T delta S, so we plug that here. And then we could do a little algebra. We get K is equal to e to the minus delta H over RT times e to delta S over R. Now if we take the natural log of both sides, we get the natural log of K is equal to minus delta H over RT plus delta S over R. Now the importance of this equation is that if we plot the natural log of the Ekman constant as a function of 1 over time, so this is inverse time on the x-axis, we get a straight line. The slope of this line is equal to minus delta H over R. And so the equation used below is to determine the temperature dependence of the Ekman constant. Remember that K equals K sub C times RT to delta N. And because we have a different number of gas particles, products, reactants, we have 2 gas particles, reactants, 1 gas particle product, K will not equal K sub C. K equals K sub C only when you have the same number of gas particles, products, and reactants. And so for endothermic reactions, delta H is greater than 0. K always increases with increase in temperature. And so that's what we're seeing here. Ekman constant is a function of temperature. This is endothermic, and so it increases exponentially. For exothermic reactions, delta H is negative because heat's going from the system to the surroundings, and K decreases with increase in temperature. So this is Ekman constant versus temperature, and you see it drop down very quickly. And so we can actually determine the Ekman constant at different temperatures using delta H and the Ekman constant at one temperature. And so if we take this equation here at 2 different temperatures and subtract one from the other, we can actually derive this equation there. And if we do a little bit more algebra, so if we take this equation, take it to the power of e, we can end up here. If you want to clean this up a little bit, you can multiply this one by T2 over T2, this one by T1 over T2, T1 over T1, give you that. And so if you have the Ekman constant at one temperature, you can actually calculate the Ekman constant at another temperature. And so this equation is actually referred to as the von Hoff equation. It was developed by von Hoff, who was actually the first one to win the Nobel Prize for chemistry. Endothermic processes. Heat is a reactant. Higher temperatures like anti-heat pushes it to produce more products. And so for endothermic processes, K increase with increase in temperature. For exothermic processes, heat is a product. Higher temperatures like adding heat pushes it to produce more reactant. And so higher temperature causes K to decrease. So whether or not K increases or decreases with higher temperature depends on if it's exothermic or if it's endothermic. I hope that helped.